In this video, we're going to talk about how to simplify and combine radical expressions. So think about if we were going to find the product of the square root of 4 times the square root of 36. Well, that's not too terrible when you think of the square root of 4 being 2 and the square root of 36 being 6 and 2 times 6 being 12. Well, our product rule for radicals tells us that you can take the square root, the nth root, of some product, a times b, and break that up into the nth root of a times the nth root of b. In this case, the square root of 4 times the square root of 36. Well, we know that 4 times 36, this is the same as the square root of 144, which we also know to be 12. So it's just a way of showing you that you can break it down, and sometimes you may not know the square root of 144 is 12, so you break it down into these two pieces that you do know, or sometimes you're still breaking it down in order to find any perfect square radicals that do exist, or perfect cubes, or whatever the radical number is. So, for example, square root of 27. That's not a perfect square number. However, I do know that 27 is the same as 9 times 3, so I can rewrite this as the square root of 9 times the square root of 3. And the square root of 9 is 3, so we can actually write square root of 27 as 3 times the square root of 3. Similarly, square root of 75, well, that's not a perfect square, but I do know that 75 is the same as 25 times 3. So we could say square root of 75 is the same as the square root of 25 times the square root of 3. Don't forget that 10. He still needs to hang out there with you. So this becomes 10 times 5 times the square root of 3, or that's 50 square root of 3. And that's how we are actually simplifying them. Okay. Fourth root of 80. Now, I don't know my perfect fourth roots off the top of my head, so I'm thinking, well, 1 to the fourth power is 1, and 2 to the fourth power is 16, so I'm going to try 16. So does 16 go into 80? Yes, it does. So this becomes the fourth root of 16 times the fourth root of 5, because 16 times 5 is 80. Don't forget this negative 1 out here in front, or negative. So then this becomes the fourth root of 16, well, that's 2, so negative 1 times 2 becomes negative 2 times the fourth root of 5 here, okay? Similarly, for this one, if I'm looking at b to the 11th, well, that's really, I'm looking at square roots here, so that's really b squared times 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 b, right? Because there I have 2, 4, 6, 8, 10, 11. And each one of these gets a square root. That wasn't a very good square root, but you get the idea. Okay, so this becomes b times b times b times b times b. And then this guy, he stays the square root of b. So this becomes b to the 5th times the square root of b. Now another way I could have thought of this, remember, is I could have said, well, this is really b to the 5th squared times b, and I'm taking the square root of that. And the square root of b to the 5th squared is b to the 5th, and then this b, he stays in here, just like that. I should probably have absolute values on this guy here in order to make sure it's positive, but we're going to see here in just a moment that from this point forward, we're going to assume that all of our variables are positive, so we're going to be okay. So thinking about 125, well, perfect square factors, that's the square root of 25 times the square root of 5. That's how we get our 125. And then x to the 7th. So you're thinking, well, how many x squareds can we bring out of there? So that's really x to the third squared, right? Because that's x to the sixth. And then I still have one extra. Okay. So then this becomes a 5. This becomes a square root of 5 still, it stays. This becomes an x to the third. And this becomes square root of x. Anything that's inside the radicals needs to stay in, and then everything on the outside can be put together. So this becomes 5, x to the third, and then I have the square root of 5 and x that stay inside the radical. And then finally, you got to think about the fifth root here. And I don't know many of my fifth roots other than 2 to the fifth, which is 32. And so this 96 happens to be 32 times 3. So this becomes 3. And then I'm doing my fifth root of 32 and my fifth root of 3, because 32 times 3 is 96. And then I'm thinking of my fifth root of x to the fifth and my fifth root of x, and then my fifth root of, let's see, I'm thinking it's going to be x to the third to the fifth, and then that's 15, so then I have 3 more left over here, right? And so, because I have 18 total there. So then this becomes a 2. So now I have a 3 times the 2. That's this guy here. I'm going to skip him for a second because I want this to stay inside my radical. This fifth root of x to the fifth, he's going to be coming out as an x. And then that's going to stay in. And then here I have the fifth root of x to the third to the fifth. So that, oh, excuse me, that should actually be y. Let's go back and fix those. I didn't catch that. If we were in class, I would have heard you say, Christina, that's a y, not an x. So sometimes you just got to shout it louder so I can hear you through the computer. So this is going to be a y to the third. And then I want to leave everything that is inside my fifth root there. So that leaves me with a 3 and an x and then a y to the third. So that's my simplified version there. Okay? So I want you to think about 150. And I want you to think about the prime factorization of 150. So we could write this as 10 times 15. And then we could write 10 as 2 times 5, which are both prime numbers. And then we could write 15 as 5 times 3, right? So when you think about 150, what we're looking for is perfect square numbers, and we get perfect square numbers, of course, from when we multiply a number times itself. So this becomes 2 times 5 squared times 3. So when I'm thinking about square root of 150, you're looking for those perfect squares that will come out, right? So if I think of this as the square root of 2 times 5 squared times 3, the only thing that I can take the square root of something squared is the 5, so he's going to come out. And then what stays inside is the 2 times 3, which is 6. So square root of 150 equals 5 square root 6. Okay. Similarly, thinking about the cube root of 320, well, if you're looking for 320, I know that that is 32 times 10, and 32 is 8 times 4, and 10 is 2 times 5. So I could write this as 4 times 2 times, this 4 would be 2 times 2, and then I have times 2 times 5, and then that 4 is an extra 2 times 2. Let me move down here just a little bit. So that's 2 times 2, and then I've got 1, 2, 3 more of them. 2 times 2 times 2 times 5. So 320 is really the same as 2 to the 5th power. I'm missing one of them. 4 times 2, 2, 2, and 2, 5. So that's 1, 2, 3, 4. I missed one down here, because this should really be 2 to the 6th power. So times 2, right? 2 to the 6th power times 5 is what I get for 320. Or, in this case, because I'm looking for the cube roots, well, this would be 2 to the 3rd times 2 to the 3rd. That's what gives me 2 to the 6th times 5. So when I'm taking the cube root of that, I'm looking for those third powers is what's going to come out, right? So 2 to the 3rd times 2 to the 3rd times 5, that gives me the 320. And then think about my a's. Well, that's going to give me an a to the 3rd and an a to the 3rd and an a to the 3rd, because that's 3, 6, 9. And then I need one more because I've got 10 total. So this 2 to the 3rd cube root, 2 to the 3rd, is a 2 on the outside. This is a 2 on the outside as well. And then I've got 1, 2, 3 of my a's that come out. And then what stays on the inside? Well, my 5 and my other a. So when all is said and done, this becomes 4 a to the 3rd and then cube root of 5a. Okay? So that's what our goal is when we're simplifying these. Prime factorization can help. Okay. Well, let's think about 153. So what goes into 153? Sure, that is really 3 times 51. And then you got to think, well, 51 is really 3 times 17. So I've got 3 times 3 times 17. So the square root of 3 squared times 17. So this gives me 3 times the square root of 17. When you're thinking about this variable, notice, let me go back for just a second. Notice when I'm doing my cube roots here, cube root of a to the 10th. What I remind students of is you're thinking how many groups of 3's are there in 10, right? So essentially what I'm saying is, what is 10 divided by 3? I've got 1, 2, 3. 10 divided by 3 is 3. And what's the remainder? 10 divided by 3 is 3 with a remainder of 1, right? So 3 a's come out, 1 a stays in. So let's remember that when we're doing this. So if I'm thinking the cube root of y to the 14th, well, what is 14 divided by 3? How many groups of 3 are in 14? Well, you're right, there are 4, right? Because 3 times 4 is 12. So I'm going to have y to the 4th come out, and then I'm left with the cube root of what's the remainder? How many stay in? Well, that'll be 2, because 14 divided by 3 is 4 with a remainder of 2. So that's how that works. Here's a couple more. 162. I'm looking for a perfect 4th root of that. Let's see. So maybe 162, that's divisible by 81, which is 3 to the 4th. So this becomes 3 to the 4th times 2 times my x to the 4th times x to the 3rd, right? So this is what I've got here. So I have a 3 and an x that come out from here and here, and then the 4th root of 2 and an x to the 3rd stay in. You get the idea here. You try this one here, thinking about what I've got. So I'm looking for perfect 5th, factors of here. When I'm thinking about y to the 12th, I think how many times does 5 go in there? And 5's going to go in there twice, so that's why I pulled out these y to the 10. And then everything else stays inside that 5th root power here. A 3 and an x and a y squared. Okay. All right. So from this point forward, for situations that aren't with functions, we're going to assume that everything is going to be positive, so we don't need any absolute values. So if when you go back to this example here, 4th root, this should be the absolute value of 3x times the fourth root of 2x to the third. Remember, because if it's an even root, we needed to put those absolute values to make sure that that stayed positive, that variable stayed positive. But from this point forward, what it's saying is, unless it's a function, we don't need to worry about those absolute value bars, okay? All right, that's the first part. Keep up the good work. We'll see you in the next video.